So here is our quotient rule, which is on your formula sheet. Here it is in Leibniz notation. Maybe I won't highlight the whole thing. I'll highlight certain parts of it. And here it is in Leibniz notation. So what we notice is we have one function. I'll highlight the top function in yellow and the bottom function in green. And unfortunately, you can't just do the derivative of the top one and the derivative of the bottom one. So you think, well, what would be the next logical thing to do? Well, let's do all of this. So here is what happens. We notice that the first thing that we do is we keep our bottom function the same. Then we do the derivative of our top function. The product rule is add, the quotient rule is subtract. Then we keep our second function the same and take the derivative of the first function. So the top part of the quotient rule looks very similar to the product rule, because the product rule was keep one the same, then do the derivative of the other one, then add and keep the other one the same and do the derivative of the other one. Okay? In some ways, when I was learning the quotient rule and the product rule, I'll just write out the product rule here. If you had f of x, g of x, the one thing that I learned about the product rule is always keep I always kept the second one the same first, because then it didn't matter which rule you were talking about, that was the same process. Because here, with the quotient rule, whatever's on the bottom, you don't take the derivative of that first, because the order matters in the quotient rule because you're subtracting. Whereas in the product rule, it really doesn't matter the order. You could keep whichever one you wanted the same first, and then the derivative of the other one, because you're adding. But now it does matter that you keep the second one the same first. And then on the bottom of your quotient rule, you keep the bottom the same again and just square it. So whatever function's on the bottom, it stays the same again. So the highlighted parts here are things that don't change. They're going to be identical to what we had to begin with. And we could do the same thing in Leibniz notation if we had a function on the top and a function on the bottom. We notice the bottom one doesn't change there, and the top one doesn't change there. So what does this look like with actual functions? This is what it would look like. We have two functions, a function on the top, a function on the bottom. We can highlight this one once we're done to show what changes, what doesn't change. And when we look at this function, we see that there's nothing that we can simplify to change this into a rule that we've done before. So when we want to take the derivative of this and get our derivative, the bottom part would stay the same. Then we would do the derivative of the top. So the derivative of x cubed is 3x squared. Then the top function stays the same, and we do the derivative of the bottom function. And the derivative of 3x minus 7 will just be 3. All over 3x minus 7 all squared. So then your bottom function gets squared. Just highlighting the things that we had here. We highlight our top function. It stayed the same here. Our bottom function, it stayed the same at the beginning, and then it stays the same on the bottom and gets squared. One thing that you'll often have in an IB exam is if they want you to simplify that, they'll ask you show that it's equal to this. One of the key things that happens in the simplification is you try to factor this as much as possible. So when I look at the top, is there something I could factor out? Is there something in common in both the first and second terms? Can you see that there's a 3x squared in both of them? And then what would you be left with if you took out that 3x squared? In the first, you would be left with 3x minus 7. In the second one, you would be left with just a minus x. So if we simplified this all the way after factoring that 3x squared out, we would be left with 2x minus 7. So sometimes it's going to be beneficial to factor it completely. So this is our final answer if we simplify it using the quotient rule. So try this one on your own. Okay, let's see how you did. So first off, if I highlight things, here's the top function, here's the top function again. Here's our bottom function. That's what we started with, and then that bottom function appears on the bottom as well when it's squared. And then if you would like to, you can expand it and simplify it. So expanding the top, combining your like terms. And in the end, that top doesn't factor. I mean, if you wanted to factor out a negative, you could. Over here on the right, I had just done each of the functions separately and done the derivatives in Leibniz notation. And the nice thing in the quotient rule is on your formula sheet. So it is a big formula and easy to forget which one goes first and which one goes second. So it's nice to know that it's on our formula sheet, that we can look at it there. Once you get to university, it won't probably be on your formula sheet. So if you want to save some time in the future and want to memorize it already, that's going to be beneficial later on. Here's the next one. This one you don't have to simplify. If you're done this one already, you can start the next one. Again, here if we highlight things, here's our top function, here's our top function, here's our bottom function, and there's our bottom function. And you're always putting the derivative of the other one with it. So this next question, you want to find the slope of the tangent at a certain point. We're not trying to find the whole equation of the tangent, just the slope of the tangent at that point. So if we're trying to find the gradient of a tangent at a certain point, first of all, remember that our derivative is the equation of every single tangent line. So when we find our derivative, that is the slope of every single tangent line for every value of x that's possible. Now, if we want to find a particular slope of a tangent line at x equals -1, then once we've simplified this, we can just plug in x equals -1 into this equation. So what I did is I took my equation. You could have plugged in -1 right away if you wanted to, but I've taken the time to simplify this expression as much as possible, and then I'll look at what happens when I plug in -1. This is where we're thankful that the question didn't say at x equals 15, because you'd have very big numbers. And once you plug that in and simplify it, you get 1. So the slope of this function at -1 is 1. I'll bring this function up on GeoGebra. We'll drag the tangent line right to -1 to see what this actually looks like. Because I don't know if you have a visual in your head of what x cubed divided by x squared plus 1 looks like, but we'll have a look at that. All right, so here's the function. Kind of is a pretty function. Now, the neat thing about an x cubed over x squared plus 1 function. So can you see that it kind of looks like a straight line with a little bit of an x cubed thing in the middle? Now, the idea behind this, sort of visualizing what this function might look like, is can you see that as x gets really, really big, this little 1 on the bottom is not going to make much of a difference? Like if x is a really large number, adding 1 on the bottom isn't going to make much of a difference. And one of the ideas of the concept of a limit is if we go to really, really big numbers, the only thing that's going to matter on the top is the x cubed, because that's the highest power. The only thing that's going to matter on the bottom is the highest power on the bottom, which is the x squared. So this means as x gets to really, really big numbers, or as x gets to really, really small numbers, if we ignore the plus 1, we would just have x cubed over x squared, which if you simplify that just becomes x. And as this function gets really, really big, can you see that it's starting to look like the line y equals x? It's only when x is small here in the middle that strange things could happen. But off at both extremes of large values of x or large negative values of x, this function is going to look like the line y equals x. But as we get closer to 0, we get a little bend in the graph. And if we plot the point right at -1 and draw that tangent, we notice the slope of that tangent is 1. And if we wanted to find the equation of that tangent line, it would be y equals x plus 0.5. Okay. How did you do on this next one? Derivative of ln x, how many people had to look back in their notes to find that one? 1 over x, yes. And the derivative of 10, secant squared. Again, you have these on your formula sheet for this year. As you move into university, they won't be on your formula sheet. Well, there won't be a formula sheet, most likely. So you would have to know the derivative of 10 is secant squared. This whole big formula book that you have for your IB exam, you're going to be expected to just know those formulas in certain university courses. And remember, when we write tan squared, we put the squared in between the tan and the x. Remember that from last year? You could also write it with brackets, but this notationally is bad because that means just the x is squared, not the whole thing is squared. This part right here, you can underline that, that's IB language. It's a show that question. It's one of the key IB command terms. Means that you have to start with this and manipulate this and get this as your final answer. So the first thing that the show that is saying is you need to show that the derivative is equal to something. So that's telling you where to start. You need to start by taking the derivative. And so we use our quotient rule, and we get our derivative. And if this was a nice show that question, after your first step, you would be done. But they don't look the same yet. But there's going to be hints built into the show that. For example, on the bottom of my function, do you see that you're going to have an x to the 4? In the top of my show that, you see that you have an x cubed. That means you're going to need to cancel out an x somehow. How do we cancel that out an x? Well, we would have to factor the top. So now the show that part is giving you hints of what you need to do moving forward to simplify this function. So moving forward, I simplify the top as much as I can. Do I have an x in common that I could factor out? Yes, I do. And once I factor that x out and simplify it, what do you know? We're happy. Super happy. Because we showed what we wanted to show. The reason the IB often has show that questions is that they'll have a next part to this question that will be much easier if you have it in this form rather than the starting form. So you can use information from the show that in the next part of the question, even if you were unable to show it in this part of the question. Oh, this doesn't appear in your book, right? I'm missing a question in between here. Okay. So example 6, I'll find it on here. So where do we have vertical asymptotes on a function? We have vertical asymptotes where we have non-permissible values. Are there any non-permissible values in this question? Yes, there are. When x is equal to 1/5, then you would be dividing by 0. So x equals 1/5 would be a vertical asymptote in this function. And now we have to find the derivative, and we need to write it in this form. So again, this is sort of like a show that question, because you're going to have to manipulate your equation until it looks like this form. And once you've manipulated your equation to look like this form, you'll be able to tell what the values of a and b are. So again, it's a derivative we need to find. So we keep the bottom the same, derivative of the top, subtract, keep the top the same, derivative of the bottom, the nice thing about the derivative this first time is we've already got the bottom in the right form. Now it's just a matter of simplifying the top, so we're going to have to expand some things here, combine our like terms. And so after combining like terms, we have things in the form ax squared plus bx. Whoa. And so we would know that a is equal to 15 and b is equal to -6. It didn't ask us to state what a and b were, it just asked us to write this in the form. So this here is our final answer in the correct form.